In recent updates, SpaceX has signaled a noticeable shift in direction. A company long defined by its ambition to send humans to Mars is now placing visible emphasis on building infrastructure on the moon. This is not a minor adjustment in messaging. For years, Mars was presented as the primary destination, the central objective that shaped Starship development, long-term architecture, and public expectations. Yet now, discussions about lunar industry, lunar settlements, and even large-scale computing infrastructure in space are moving to the forefront. The mission has not changed, but the path toward it appears to be evolving. So what exactly is happening, and why does it matter? So let's take a closer look. If you value clear, step-by-step explanations of complex space developments without hype or speculation, consider supporting the channel so you don't miss future breakdowns. The shift became clear through a series of recent statements and updates from SpaceX leadership, including comments attributed directly to Elon Musk. In these updates, SpaceX confirmed that it is prioritizing the development of a sustained presence on the moon before committing full-scale resources to a long-term Mars settlement. This does not mean Mars has been abandoned. Public statements still reaffirm the goal of building a self-sustaining city on Mars within the next several years. However, operational emphasis, including infrastructure planning, cargo delivery strategy, and industrial concepts, now appears more closely aligned with lunar development. The reasoning presented centers on practicality and timelines. According to these updates, establishing a meaningful industrial foothold on the moon could potentially be achieved in under a decade. By comparison, constructing a comparable settlement architecture on Mars is projected to require 20 years or more. The update also introduced an additional dimension: the possibility of building large-scale computing and manufacturing infrastructure in space, potentially using the moon as a staging and production platform. Starship's heavy lift capability and in-space refueling, meaning the ability to transfer propellant between spacecraft while in orbit, are positioned as enabling technologies for this shift. At the same time, SpaceX continues expanding its launch infrastructure at Starbase in Texas. Regulatory approvals now allow additional land development for launch pads and support facilities, reinforcing the company's preparation for higher launch cadence and larger-scale operations. Taken together, these developments suggest not a change in mission, but a recalibration of sequence. To understand why this shift makes operational sense, we need to examine the technical constraints that shape missions to Mars and compare them directly with missions to the moon. The first factor is orbital mechanics. Orbital mechanics is the branch of physics that describes how objects move under gravity, including planets and spacecraft. When traveling between planets, spacecraft do not fly in straight lines. They move along carefully calculated transfer orbits that minimize energy use. The key measurement here is called delta 5. Delta 5 refers to the total change in velocity a spacecraft must achieve to complete a mission. In simple terms, it represents how much propulsion energy is required. The higher the delta V, the more fuel and mass a mission demands. For Mars missions, delta V requirements depend heavily on planetary alignment. Earth and Mars do not stay in fixed positions relative to one another. They orbit the Sun at different speeds. The interval at which they return to the same relative configuration is called the synodic period, and for Earth and Mars, it occurs approximately every 26 months. This means launch opportunities to Mars are limited. If a mission misses its optimal window, it may need to wait more than 2 years for the next efficient opportunity. That alone slows iteration. Even within these windows, not all opportunities are equal. Mars follows an elliptical, or slightly elongated orbit. Because of this, the distance between Earth and Mars varies significantly. Some alignment periods require nearly twice the energy of the most favorable alignments. These variations follow longer cycles of roughly 15 years. The most energy-efficient transfer trajectory to Mars is called a Hohmann transfer orbit. A Hohmann transfer is a two-burn maneuver that moves a spacecraft from one circular orbit to another using the least possible energy. For Earth to Mars missions, this approach typically requires about 9 months of travel time to reach Mars. However, arrival is only part of the mission. A crewed mission must also wait for the next favorable alignment to return home. That waiting period can last around 500 days. Then, the spacecraft requires another 9 months to return to Earth. In total, this standard conjunction-class mission lasts roughly 34 months. Faster mission profiles exist. An opposition-class mission reduces total time to around 400 to 450 days. But doing so requires significantly higher delta VAI, meaning much more fuel and engineering complexity. Even more aggressive mission profiles, sometimes discussed at around 245 days round trip, would demand advanced techniques such as on-orbit staging and extremely high propulsion performance. These approaches push technological and economic practicality. Now compare this to the Moon. The Moon orbits Earth once every 27 days. Launch windows to the Moon are therefore frequent. In practice, missions can depart roughly every 10 days. Transit time is short, approximately 2 days from Earth to lunar orbit. This single difference changes the development model. Instead of waiting 26 months between major launch windows, a lunar program can test hardware repeatedly within weeks. If a system fails, engineers can redesign and attempt again within days. This dramatically increases iteration speed. The second major factor is communication latency. All communication signals travel at the speed of light. The farther the destination, the longer the delay. For the Moon, the round-trip communication delay is about 2.5 seconds. That delay is noticeable but manageable. Near real-time remote control is possible. For Mars, signal delay varies between 4 and 24 minutes one way, depending on orbital positions. During the landing of the Curiosity rover, the one-way delay was approximately 13 minutes and 48 seconds. That means mission control could not intervene in real time. Every landing sequence had to be fully autonomous. For crewed operations, communication delay affects decision-making, troubleshooting, and psychological factors. A few seconds of delay is workable. Several minutes removes immediate feedback entirely. The third factor is emergency response and resupply. If a major systems failure occurs on the Moon, a rescue mission could potentially arrive within days. Cargo resupply can occur frequently. This reduces risk exposure during early infrastructure development. For Mars, once a crew departs Earth, external assistance is effectively unavailable for months or even years. Any critical failure must be handled locally. Now consider environmental factors. Gravity plays a significant role in human health. Earth's gravity is defined as 1g. The Moon provides about 0.165 g, roughly 16.5% of Earth's gravity. Mars provides about 0.38 grams, or 38% of Earth's gravity. Long-term exposure to microgravity is known to cause bone density loss, muscle atrophy, cardiovascular changes, and immune system effects. The long-term health consequences of partial gravity are not fully understood. However, higher gravity is generally assumed to be more favorable than lower gravity. Atmosphere is another difference. The Moon has no atmosphere. Mars has a thin atmosphere composed mostly of carbon dioxide. Although it is too thin for breathing, it provides some radiation shielding and can be processed for useful gases. This connects to a concept called in situ resource utilization, or ISRU. ISRU refers to using local materials at a destination instead of transporting everything from Earth. Mars offers accessible water ice and an atmosphere rich in carbon dioxide. Carbon dioxide can be chemically processed with water through reactions such as the Sabatier process to produce methane and oxygen. Methane and oxygen are the propellants used by Starship. This alignment reduces dependency on Earth resupply. The Moon also contains useful materials, including oxygen bound within lunar regolith, the layer of loose surface material. However, extracting usable resources from lunar regolith requires high-energy processing. Additionally, the Moon's permanently shadowed regions, where water ice may exist, can reach extremely low temperatures, complicating operations. Dust is another technical concern. Lunar dust particles are sharp and electrostatically charged. During Apollo missions, dust caused abrasion, seal damage, and equipment degradation in only a few days of surface activity. Martian dust, shaped by atmospheric weathering, is less jagged, though still challenging. Day-night cycles also differ significantly. Mars has a rotational period of 24 hours and 40 minutes, very close to Earth's day. The Moon experiences a full day-night cycle over roughly 28 Earth days, meaning approximately 14 days of continuous sunlight followed by 14 days of darkness. Long periods without sunlight complicate solar power generation and thermal control. Taken together, these technical factors show a pattern. The Moon offers faster iteration, closer support, and lower logistical risk. Mars offers stronger long-term environmental characteristics for independent settlement, but at the cost of higher complexity, longer timelines, and greater exposure to mission risk. Understanding this contrast clarifies why operational focus might shift without changing the ultimate destination. The technical comparison explains how the Moon and Mars differ, but the more important question is strategic. What does this shift mean for the long-term architecture of human expansion into space? For decades, government space agencies have treated the Moon as a stepping stone. Programs like Artemis are structured around returning astronauts to the lunar surface, building sustainable infrastructure, and learning how to operate beyond low Earth orbit for extended periods. In that framework, the Moon is not the final destination. It is a proving ground. SpaceX's recalibration appears to align with that logic, but from a commercial and industrial perspective. If a company can test life support systems, surface power generation, habitat construction, cargo landing techniques, and resource extraction within days of Earth, rather than months away, development cycles shorten dramatically. Failures become survivable events rather than catastrophic setbacks. This has implications for capital efficiency. Interplanetary missions require enormous upfront investment. A program that can iterate quickly may reduce the time between design, test, failure, redesign, and validation. In engineering, that cycle speed often determines which systems mature first. There is also a second strategic layer introduced in the recent updates. Space-based industry linked to artificial intelligence infrastructure. Modern AI systems require large-scale data centers. Data centers require electricity and cooling. On Earth, both are constrained by grid capacity, environmental regulation, and physical land availability. Space, by contrast, offers near-continuous solar exposure and effectively unlimited expansion potential. If Starship achieves its intended payload capacity, meaning it can lift massive amounts of cargo per launch, it could reduce the cost per kilogram delivered to space. Lower transport cost changes what is economically viable. From this perspective, the Moon could function as an industrial platform. Low gravity reduces the energy required to launch manufactured products into orbit. The absence of atmosphere eliminates aerodynamic constraints. Electromagnetic mass drivers, systems that accelerate payloads using electrical force instead of combustion, become more practical in such an environment. If lunar factories could use local materials to build satellites or other infrastructure components, dependence on Earth-based manufacturing would decrease. And if those satellites were part of a larger energy harvesting or computational network, the moon would become more than a test site. It would become part of an economic system in space. This does not eliminate Mars from the picture. If the ultimate objective is a self-sustaining civilization beyond Earth, Mars retains key advantages: higher gravity, atmospheric resources, and more Earth-like day cycles. But building a permanent settlement requires stable supply chains, reliable life support systems, and validated industrial processes. If those systems can be refined on the moon first, risk on Mars may decrease. In this interpretation, the shift is not about abandoning Mars. It is about sequencing development differently. If the moon enables faster learning and earlier industrialization, then it may accelerate, rather than delay, long-term interplanetary goals. Despite the clear emphasis on lunar development, several uncertainties remain. First, timelines. Statements suggesting that a meaningful lunar presence could be achieved within a decade are projections, not guarantees. Large-scale space infrastructure depends on sustained funding, regulatory stability, technical reliability, and launch cadence. Starship itself, the central vehicle enabling this architecture, is still in an active development and testing phase. Its long-term reusability, orbital refueling capability, and payload delivery rates will determine whether lunar industrial concepts move from theory to execution. Second, the economic model of space-based AI infrastructure remains largely conceptual. While the technical logic of abundant solar energy in space is sound, questions remain about construction costs, maintenance complexity, radiation shielding for electronics, and long-term operational sustainability. None of these challenges are insurmountable, but they require demonstrated engineering solutions. Third, Mars has not disappeared from the roadmap. Public statements continue to reaffirm intentions to begin building a Martian city within the next several years. However, interplanetary missions depend heavily on launch readiness, life support validation, and resource utilization systems that are not yet fully proven at scale. The first crewed Mars mission will likely hinge on lessons learned elsewhere. In the near term, several milestones are worth watching. Further Starship test flights will indicate whether full reusability and in-space propellant transfer become routine. Increased launch cadence at Starbase will signal whether infrastructure expansion translates into operational capability. Lunar mission contracts, both governmental and commercial, may clarify how quickly surface operations can begin. None of these developments guarantees a permanent settlement on the Moon or Mars, but each will reveal whether the sequence now unfolding is sustainable. For now, what we are witnessing is not a retreat from Mars, nor a simple pivot to the Moon. It is a restructuring of priorities around feasibility and iteration. And as new data emerges, from launch results to lunar mission deployments, the direction will become clearer. If you're following how these long-term ambitions translate into real-world engineering milestones, future developments will likely provide important signals.